So, hi guys. In the previous lecture, we introduced the idea of feedback and we looked at from a historic perspective how did the engineers who were first working on the problem of feedback chanced upon the concept of feedback. Now, I'll very quickly take you through what are the benefits that feedback offers and what are the benefits that are exclusive to feedback. I mean, you don't get those benefits if you don't go for feedback. And then we will also discuss some other rather unintended benefits that you get out of feedback, but you don't necessarily need to use feedback to get those benefits. So, what are those? We are going to discuss in this lecture very briefly. So, first, that main advantage, one of the fundamental advantages of negative feedback is gain desensitization. Meaning, if I want to build an amplifier with a fixed gain, we said that the manufacturing processes and also the engineers, when they were building the first vacuum tube amplifiers, the parameters were drifting with time, which means the gains were changing with time. But by using feedback, as long as we ensure this condition, A beta is much greater than 1, we can ensure that the closed loop gain will be nearly constant. One of the fundamental ideas that you have to keep in mind when we are discussing negative feedback is that it's assumed that this factor beta is constant. This is not changing with temperature or time. Only then you get that advantage because of this beta that can be designed or which you can actually have with almost negligible variations with external conditions or temperature and process. If you can have something of that is fixed in nature, then using negative feedback we can actually design an amplifier with a near constant gain. So now what we'll do is we'll try to compare the fractional variation in the gain. Let delta A by A be the fractional or the percentage variation. You get it by multiplying it by 100, you get the percentage variation in gain for the amplifier in open loop. We'll try to find out if I use this amplifier in the forward path of your negative feedback amplifier, what will be the fractional change in delta closed loop, that is your ACL by delta ACL by ACL. So ACL here is given by A upon 1 plus A beta. A here is your open loop or the forward path transfer function. Beta is your feedback factor. We said that if we can feed the signal, the output signal back to the input, back to the forward amplifier, then we get a lot of advantages out of this. So the expression for the gain, if I take A beta common out, we can also express the closed loop gain in terms of beta, in terms of the gain 1 by beta as the factor 1 by beta into 1 by 1 plus 1 by A beta. And if this factor A beta is much greater than 1, even though A is changing significantly, let it change by 10 times, we assumed a variation of plus 900% to minus 90%. So we assumed a variation of 10A to A by 10, and then even then, as long as A beta is much greater than 1, we said this term will be very close to 1. So that's how we said we get a near constant gain in a negative feedback amplifier. Now to quantify it better, how much advantage are we really getting in comparison with the open loop or in comparison with an open loop amplifier? Let A be the gain of an open loop amplifier. If delta A by A is the fractional change in the gain multiplied by 100, that will be your percentage change in the open loop gain. So delta AOL by AOL here is your open loop gain, which is nothing but the forward gain of the amplifier, which is simply delta A by A itself. Now we'll try to calculate what is the percentage change or the fractional change in the closed loop gain. Your closed loop gain is given by A by 1 plus A beta. Now remember, the only parameter that's going to change here is A here. Beta is constant. A is the only parameter which is changing. So then what I'm going to do is that I'm going to differentiate this term with respect to A. So if I want to find incremental changes or change in delta ACL, that's because of the change due to the change in A, I'll have to differentiate this expression with respect to delta A and find out that value. So this I can write it as change in this term, keeping this term, I mean this is like differentiation by parts. So I'll find delta A into 1 by 1 plus A beta minus A into change in 1 by 1 plus A beta. So you have to differentiate this. So you will get minus of 1 by A 1 plus A beta the whole square multiplied by delta of A beta. So beta is fixed, so it will be beta times delta A. So that's what I've written here. You get an expression A beta by 1 plus A beta whole square into delta A, and the first term will be delta A upon 1 by A 1 plus A beta. So this directly follows from differentiation by parts. So I'll take delta A by 1 plus A beta common out. I'll be left with 1 minus A beta by 1 plus A beta. This term will reduce to 1 by 1 plus A beta. So all I need to do is multiply and divide by A. So I'm going to get delta A by A into A by 1 plus A beta, this term, into 1 by 1 plus A beta. Now this term here, A by 1 plus A beta, is nothing but your closed loop gain ACL. So if you take this term to this side, you will get delta A by ACL, which is the fractional change in the closed loop gain, will be equal to the fractional change in the open loop gain multiplied by 1 by 1 plus A beta. So this is the expression we get for the percentage change in the closed loop gain in terms of the percentage change in the open loop gain. So what we are seeing here is that even though your open loop gain can change by a huge ratio, by a huge factor, it gets divided by 1 plus A beta. So if A beta is much greater than 1, then the variation in your closed loop gain is reduced significantly. So this advantage is what we call gain desensitization. The gain is more or less insensitive, or rather it doesn't change with process or temperature variations, even though your open loop amplifier's gain is changing significantly. Now you get these benefits. To be very clear, to reiterate, you get all these benefits as long as you maintain this condition, which is A beta has to be much greater than 1. Now this is one of the important advantages of negative feedback, gain desensitization, and I said this is the reason why negative feedback is so popular even after 100 years since its invention. Now we'll look at the other main benefit which was claimed by the inventors of negative feedback. If you remember, when they were starting to find or come up with this idea of negative feedback, the engineer, especially Harold S. Black, he was working on this problem of distortion reduction. So it's not a very easy advantage to understand why is the distortion advantage coming from going for negative feedback. So that's why I'll spend some time and we'll do a proper apples to apple comparison between an open loop amplifier and a closed loop amplifier with the same gain and see which one offers a lower distortion. So the question is, why does distortion arise in the first place? What is the source of distortion in amplifiers? We said that all amplifiers, which will give us a very high voltage gain, are fundamentally built using devices with nonlinear transfer characteristics. A vacuum tube amplifier, a MOSFET, or a BJT. Vacuum tube amplifier, the zeroth order model, the current and voltage are related to power 3 by 2. In case of a BJT, it's an exponential device. Current is proportional to exponential of voltage applied across it, across the base emitter junction. And in case of a MOSFET, it's a square law device. Okay, so these are nonlinear functions, but we are trying to build linear circuits using them, and the linearity conditions hold true for small signals. So generally, let's assume your linearity is y equals f of x is given by k1x minus k3x cubed. I've assumed a simple nonlinearity model. So if I try to plot this function, it's going to look like this. So this is for x greater than, when you keep increasing x initially, the first term will be greater than the second term. So this is a linear term. So if I draw this linear term, k1x will look like this. k3x cube, on the other hand, its slope will be 0 at x equal to 0. So it will slightly be a flatter curve and it will cross the linear function after some point. At some point, both the terms will become equal. That's what this function, what I've shown here. So when both these terms become equal, you get this graph here. So this graph is k1x minus this graph, which is k3x cube, you will get this function. I mean, this function will go negative, this will go positive. But this function models nonlinear amplifiers to good extent as long as we restrict your inputs to this range. If you restrict your input to this range, it shows as though the gain is decreasing as you increase your input signal. After a point, at this point, the slope becomes zero. At that point, your gain has become zero, right? So this is a very good approximation for modeling the nonlinearity in an amplifier. So now if you look at this equation, what we see here is that if I inject a signal of frequency cos omega naught t, x is cos omega naught t, because of this term x cube of t, you will also get a term cos of 3 omega naught t. Now this here is distortion. So this term is called nonlinear distortion. Distortion arising because of the amplifier's nonlinearities. Now this is what they wanted to suppress or reduce. The first engineers who were building these amplifiers for telephone communications, they wanted to suppress or reduce this term. One way is to build a linear amplifier itself, make an amplifier as linear as possible. We will later see, probably in the next semester's course, to build a linear amplifier, we have to burn more power or you need a higher supply voltage. So we'll see what are the trade-offs there. Now, given that you have a nonlinear amplifier, can you somehow reduce distortion? And we saw for the first time how Harold S. Black employed the idea of feed-forward cancellation. You measure the unwanted terms and then subtract it out. You can do that for nonlinearity. And so that idea, it had a problem. We had to match the gains and it needed some kind of tweaking to ensure that the cancellation path was always ensuring that the cancellation path gain was matching the main path gain. So that we'll not go there right now. We'll try to understand how negative feedback, which I'm going to show in a few moments, tries to actually suppress the nonlinearity generated because of this guy. Before we go to that, I'll just quickly revise some other benefits of negative feedback. So this was also, in fact, Harold S. Black claimed nearly in the order of 200 advantages for negative feedback. So in his patent claim, he claimed there are 200 benefits, for more than 200 benefits for negative feedback amplifiers. One of those benefits was its response to disturbances. If you add an external disturbance, the amplifier, maybe the supply in the amplifier is adding some external noise, so I'm modeling it as external noise. We can model it as an external noise contributed because of this amplifier. Okay, so this can be from the supply. So because he was building this amplifier using vacuum tube amplifiers, and he claimed that the supply noise of these amplifiers can also be rejected. So he assumed that N to be the noise added by this amplifier, and he called them as external disturbances. And now let's see how does this negative feedback amplifier reacts to external disturbances. In open loop, if I'm going to feed X, your Y is simply going to be A times X plus N. So your external disturbance is going to directly appear at the output. But now we will see, because remember that this external disturbance is added only by the forward amplifier. Feedback is not adding any external disturbance. So only forward amplifier is adding this. So we'll now see what will happen to the output Y because of this external disturbance. Now we'll assume that this external disturbance is independent of the input. It's independent. So because they're independent, I can apply the principle of superposition. So first I'm going to assume the noise here is 0 and assume only input is present. In that case, if the noise is 0, it just reduces to a simple negative feedback amplifier. So the gain of that is A by 1 plus A beta times X. So that's your output Y. Now in the second case, I'm going to assume the input X is 0 and noise N is present. Now I'll have to redraw the model a little bit so that we can reduce it to a more familiar form. So here the forward path gain from N to Y is 1. Now what I can do is here, I can remove the summation here. I can remove the summation and take this negative sign. So I can remove the summation here and take this negative sign to this part, or you can bring it to this side also. Or I can directly shift this negative to this point here. In the summer, instead of adding the 2, I can subtract it. So that's what I've done here now in the next, reduced form of this closed loop model. In the forward path, the gain is 1. So that's 1 here. The whole thing comes in feedback now. So beta is in feedback, A is also in feedback, that gets subtracted here. Now this happens to be your reduced control model, loop model for this, for the external disturbances N. Now you know this model, so immediately you can write the transfer function. The forward path gain is 1 divided by 1 plus loop gain. Loop gain here is still the same, A into beta, so you get this. So this is true for a negative feedback. Since it is negative here, it's a negative feedback, so you get the plus sign here. If it's a positive feedback, if the plus sign is plus there, you will get minus. You'll get 1 by 1 minus A beta. So now I'll add the two outputs. You get y as x into a by 1 plus a beta plus n into 1 by 1 plus a beta. So if you see here, as far as x is concerned, the transfer function is much higher. It is a by 1 plus a beta, but for n, it is a times lower than what it was for x. It is just 1 by 1 plus a beta. Now if a beta tends to infinity, if a beta is really much larger, then this term here, a by 1 plus a beta will become 1 by beta, and this term 1 by a plus beta, 1 by 1 plus a beta will tend to 0. So you'll be left with y equals x by a beta, x by beta. So what we can see here is that if your loop gain a beta is much greater than 1, negative feedback has a tendency to completely eliminate external disturbances. So when I say external disturbances because of this amplifier, if you add it at this point. Okay, its external disturbances are getting added to the output of this amplifier. These are external sources, we don't have control over them, but negative feedback suppresses them as well. Now we'll keep this point in mind. This will be very helpful in understanding the nonlinear distortion direction. So remember, I said we have to make an apple-to-apple comparison when we are comparing nonlinear distortion. So that's why I'm just spending so much of explanation just to drive that point home, that you have to make a very clear-cut comparison. A lot of textbooks don't do the comparison in the right way. So which is why we are trying to do that now. I mean, the reasoning for all this so far, what we introduced so far, is so that we can understand the process of comparison better. Now let's say you're tasked with designing an amplifier with a gain of 100. Right now, I don't care about process or time variations with the gain. I don't care about gain varying with time or process. I'm only interested in distortion reduction. And I'm telling you, a nonlinear amplifier has a nonlinearity given, characteristic given by this. It is y equals 100x minus 0.1x cubed. So this is the transfer characteristics. It's a nonlinear function given by this. So from this you can clearly see, if you ignore for small signals, so can you tell me what will be the DC gain? Gain for small signals? So what will be the gain for the small signals? 100, right? You immediately see that? It's 100 for small signals. I can assume x is so small that I can neglect this quantity, and the gain for small signals will just be 100 itself. So that's what we have designed. We have started to design an amplifier with a gain of 100, but it also comes with a nonlinear term. Now I'm going to feed an input of this type, x equals cos omega naught t. If I feed an input of this type, x equal to cos omega naught t, what will happen here? You're going to get 100 cos omega naught t, because that's because of the input directly, the linear term. But you will also have another term minus of 0.1 into cos cube omega naught t. Now I'll use the simple expansion. Cos cube theta can be written as 3/4 cos theta plus 1/4 cos 3 theta. I think a more familiar expression, most of you will be familiar with cos 3 theta, is 4 cos cube theta minus 3 cos theta. So from this we can write an expression for cos cube theta as 3/4 cos theta and 1/4 cos 3 theta. So now if I use that, I can write this expression as 0.1 by 4 cos 3 omega naught t, plus you'll also have 3/4 0.1 cos omega naught t. So that's what I've written here. Now this term is negligibly small in comparison with 100, so I'll ignore this term. So I'll only consider this. So now if you see, the output contains two frequencies. You are looking for the output, you fed an input of frequency omega naught, but now this I can approximate it to 100 cos omega naught t minus 0.1 by 4 cos 3 omega naught t. Of course, this term is in much smaller magnitude, but still you have an unwanted component present. So if I take the Fourier transform of the output, You will see two impulses. I'm drawing only the positive frequencies. One impulse at omega naught, the other impulse at 3 omega naught. So this term here is distortion. You don't want this to be present at the output. For a linear system, there should be no 3 omega naught, but it's present because of a non-linearities in the amplifier. So we want this term to be reduced. Now what I'll do is, I'm just to tell how this nonlinearity behaves. So right now the amplitude here is 100 and this amplitude here is 0.1 by 4. Now I'm going to feed a sine wave of amplitude 1/10 of what it was previously. I'm going to feed a sine wave of amplitude 0.1. So if I feed an amplitude of 0.1, the characteristics is 100x minus 0.1 x cube. So if you feed it, what I'm going to get is 0.1 into 10, so 100 it will be 10 cos omega naught t minus 0.1 into 0.1 whole cube. So this is 0.1 into x cube, x is 0.1 whole cube cos cube theta, cos cube 3 omega naught t. So this term here becomes 10 power minus 3 by 4. Again, I'm ignoring the 3/4 cos theta term. That's a much smaller value compared to 10. So you'll be left with 10 cos omega naught t minus 10 power minus 3 by 4 into cos omega naught 3 omega naught t. Now if I take its Fourier transform and plot it, the first harmonic magnitude is 10. The third harmonic magnitude, on the other hand, it becomes 0.1 by 4 into 1 by 100, or 0.1 the whole square. So 0.1 the whole square. So if I reduce my input signal amplitude by 10 times, what am I seeing here is that, of course, the main lobe reduces by it will be 0.1 into cube. This is 10 power minus 4 here. So this is 0.1 the whole cube. So if the main amplitude, if I'm going to reduce my amplitude of the input signal by a factor of 10, the first harmonic strength is going to reduce by a factor of 10. By how much does the third harmonic strength reduce? It reduces by 10 cube, 1000 times. It reduces by 1000 times. So that's why if you reduce your signal level, the harmonic levels will decrease significantly. I can also say in the other way, if I increase my signal level by 10 times, if I increase it by 10 times, how much does the third harmonic increase? By what will be the magnitude by which it increases? 1000 times, right? It increases by 10 cube times. So that's why. So if you reduce your signal level, you will see a significant reduction in the harmonic terms. So it's a very simple result. If you actually have an nth order harmonic, let's assume you have an nth order harmonic, then if you reduce your input signal amplitude by n times, or let's say 10 times, what will be the power by which you think your nth harmonic will go down by? 10 power n times, right? 10 power n, because if I reduce it by 10 times, it will go down by 10 power n times. Okay, so that's something you have to keep in mind. Now, using this knowledge and the response, how does that feedback system respond to, the external disturbances? We'll now try to understand how does a negative feedback amplifier respond to non-linearities, or rather, the nonlinear distortion. What we saw so far in case of linear distortion, we saw that we are at the mercy of the nonlinearity of the amplifier. If it generates some nonlinear term, which will be 0.1 by 4 cos cube omega naught t, we have cos 3 omega naught t, we have to live with this. Okay? The only way, as a designer, you will try to reduce this nonlinear term as much as you can, but after that, you are at the mercy of the amplifier's characteristic. Now, what I'll do is, I can actually represent, or rather, let me just, come back to this point, which is the presence of this nonlinearity. What does it do to your signal? So you'll have a main term, which is the intended signal of interest, which you want to amplify. In addition to that, I've shown 3 omega naught here. So this frequency is omega naught. So in one cycle, if you see the high frequency signal undergoes 3 cycles. So it's a signal of frequency 3 omega naught. Both the frequencies are present. This term is distortion. It affects the quality of your signal. Okay, it affects the quality of your signal. The lower this term is, the better your quality of your signal is. Now, I began with the problem. I said you need an amplifier, you need an amplifier with a gain of 100. That's your goal to design. Now, I'll try to realize an amplifier with a gain of 100 using negative feedback. So to get a gain of amplifier 100, what should be your beta? What should be the value of beta if I want to get a gain of 100? Approximately the closed loop gain is 1 by beta. It should be 0.01 or 1 by 100. Your beta should be 1 by 100. If your beta is 1 by 100, then your closed loop gain is approximately 1 by beta. So then you get 100. Now, I have to ensure if I have to use negative feedback, then I have to ensure the forward path gain or the product A into beta is much greater than 1. That condition has to be always ensured. So from this, what do you think should be the value of A? What do I need A to be? It has to be much greater than 100, right? Because A beta has to be much greater than 1. So A has to be much greater than 100. So which is why if you see in this example, what I have done here, I have cascaded 3 such nonlinear amplifiers. I have taken these 3 amplifiers and I have cascaded them. Okay, so I have cascaded them in the hopes that I'll be able to get a much larger loop gain. Now, what is the loop gain for this amplifier? The loop gain in this amplifier is A cube into beta. That's your loop gain. A cube into beta. So if A is 100, A cube is 10 power 6 and beta is say 1 by 100. So you get A beta is 10 power 4. A cube beta is 10 power 4. So now I have a sufficiently large loop gain. So I can use this amplifier in negative feedback. So if I use this amplifier in negative feedback, so I'm going to have the gain, closed loop gain is going to be 100. So now let's look at this amplifier here and let's look at how much nonlinearity does each amplifier experience. So I've cascaded 3 identical amplifiers. This was an open loop in the first case and the characteristics was given by this. Now let's look at it. If I have negative feedback, let's say it's a negative feedback amplifier, I'm feeding an amplifier, let's say I'm feeding a sinusoid with an amplitude of 1 volt. Amplitude is 1 volt, peak to peak is 2 volts. I'm feeding it as an input here. What do you think will be the output amplitude? What will be this amplitude here? Beta is 100, 1 by 100. Keep that in mind. What will be the amplitude, output amplitude roughly? The first harmonic amplitude of the first harmonic. 200 peak to peak or amplitude will be 100. Do you see that? I have fed a sine wave of 1 volt amplitude. If I fed a sine wave of 1 volt amplitude, the gain is going to be 100. So this will be 100. So now if you tell me this, if the amplitude at this point is 100, what will be the amplitude at this node? Amplitude of this final amplifier's output is 100. The input to that, what will be the amplitude? 10. No, its gain is 100. The gain is 100, so it will be 1. Yes. This input amplitude will be 1. What will be the amplitude at this point? The input amplitude of the second amplifier. 0.1, right? Or 0.01. It is 1 by 100, 0.01. And the input at this amplifier here is 10 power minus 4, which is approximately 0. Now you tell me, which amplifier's nonlinearity do you think matters the most? Which amplifier's nonlinearity matters the most? The first amplifier's input is negligibly small. So of course he's contributing some nonlinearity here, but I'll ignore it. Second amplifier is also contributing to some nonlinearity, but I'm also going to say it's negligibly small. So I'll ignore it. But the third one is going to contribute significant nonlinearity. So I can't ignore it. So I'll consider that. Now, do you see something interesting here? Is that the final amplifier, if you look at the final amplifier, it's seeing similar conditions as an open loop amplifier. The gain of an open loop amplifier was 100. And we were feeding a 1 volt input amplitude for the open loop amplifier. It's very similar. The only difference, there is only one difference in negative feedback. There is an external feedback loop, which is absent in an open loop amplifier. But otherwise, everything else looks the same. Now, what I'm going to do is that, because it's a nonlinear amplifier, I'm feeding a sine wave of amplitude omega naught, frequency omega naught. At the output, I'm getting a different signal with frequency 3 omega naught. So what I'm going to do, I'm going to model this nonlinear amplifier with characteristics f of x as an amplifier as an amplifier with a linear gain 100. I'm going to model it as a linear amplifier with a gain of 100, and an additive noise whose amplitude is given by A3. A3 here will be K3A cube. Okay, K3A cube cos omega naught. So I'm just writing K3. A3 here is K3 into A cube. I'm modeling this as an external noise, external disturbance. So the output here will contain two terms. One term will be A 100 times cos omega naught t. The second term will be, I can maybe subtract or add, it doesn't matter. I can subtract it or add it depending on polarity. Will be minus of A3 cos 3 omega naught t. And A3, I can choose it to be, K3 times A cube, where A here, A in cube, where A in here is your input signal's amplitude. I can approximate it this way. So is this fine? I've modeled mathematically the non-linearity as an external disturbance. Mathematically, I'm capturing it. See, if I feed a signal of amplitude 1 volt here, I'm going to get 1 volt plus an unwanted term. Now, what I'm saying is I'm going to split this non-linearity into two parts and model this as an external disturbance. So that's the mathematical model. If the amplifier is an open loop, in open loop, this external disturbance appears directly at the output. It appears directly at the output. There is nothing done to that. It appears directly at the output. Okay. So we said that if you measure, you're going to see a sinusoid with an amplitude, let's say input amplitude is 1, you will see 100, and the other guy is going to be 0.1 by 4. That's the amplitude for 3 omega naught. This we just discussed it for a few moments ago. Now we'll see what happens in negative feedback. I'm going to replace this amplifier with this linear model. Linear model plus an additive noise because of distortion. That's what I've shown here. I've replaced this amplifier. I'm going to assume these two are linear because the additive components are so small. I'm neglecting those additive components, and I've replaced it with a linear model. Now these amplifiers, all these three amplifiers are linear amplifiers, and the nonlinear term is being added as a distortion term at this point. Now can you tell me what will be the transfer function from this point to the output y? Output y here. So this is the output y at this point. Remember, I'm feeding an input of signal of this type. A1 cos omega naught t. This is the input I'm feeding. A3 cos 3 omega naught t. That's your external disturbance in the last amplifier. Now, we have already analyzed this problem. If you have two inputs here, A1 cos omega naught t, which is the input signal of interest. This is A3 cos 3 omega naught t, which is the unwanted signal. Then we already derived an expression for this. We are going to get the transfer function for this guy will be for the input which is A1 cos omega naught t will be the forward path gain, which will be A cube divided by 1 plus A cube beta, which is what I've shown here. For the noise, for the disturbance here, the transfer function is going to be A3, this is your signal, A3 cos 3 omega naught t into 1 by 1 plus A cube beta. Now see this is the hallmark of negative feedback amplifiers. The input signal, approximately if I assume A cube beta is much greater than 1, it's going to be A1 cos omega naught t into 1 by beta. That is getting multiplied by a factor of 100, which is beta is 100. So you're getting an amplitude of 100 here. But what happened to the 3 omega naught? 3 omega naught is now A3 divided by A cube beta. A cube beta, what is the value of A cube beta for the example we assumed? Beta is 1 by 100, so it's 10 power 4. So previously this was 0.1 by 4, but now it is getting reduced by a factor of 10 power 4. That's a huge advantage. So in terms of decibels, if I ask you how many decibels are we gaining, it will be 20 log of 10 power 4, it will be 80 decibels. Compared to closed loop, compared to open loop, you will have a third harmonic will be 80 decibels lower. That's the major advantage of negative feedback amplifiers. This is the advantage you get in negative feedback amplifiers, which you don't get in open loop amplifiers. Okay, so this is one of the major advantages. This was the claim which Harold S. Black made when he designed the first amplifier, because to begin with, he wanted to solve this problem. He wanted to get rid of harmonics or reduce it as much as he can. And using negative feedback, he could reduce it significantly. Not this, his mathematical analysis was a little bit more involved, but what he could show was he could reduce it by a factor of 20 log of 1 plus a beta. So he said by going to negative feedback, not only do you get a constant and near constant closed loop gain, but you also can suppress harmonics significantly. Distortion can be reduced. So that's why if you see the claims made, these are the two major claims that negative feedback makes. I mean, the inventors of negative feedback made. One, desensitization, gain desensitization. Gain remains nearly constant even with time, even with process, temperature. Even though the open loop parameters are changing, as long as A beta is much greater than 1, the closed loop gain remains nearly constant. And that was one of the major benefits. In addition to that, distortion also gets reduced significantly. That was the second major claim of negative feedback amplifiers. And these are the two major advantages you will get out of negative feedback amplifiers. The other benefits that you might get out of, we will see a little bit more, rather we will look at what happens at the input and output impedances. Other benefits, you don't have to go to negative feedback to get them, okay? But you get it as an advantage, or rather you get it as some kind of, you get it because of negative feedback, you get it for free. But you don't necessarily design negative feedback to get those advantages. Okay, when I say those advantages, I'm going to discuss what those advantages are at a later stage. Okay, so what we have discussed now is non-linearity and what are the advantages we are getting as far as non-linearity is concerned by going for negative feedback amplifiers. Okay, I'll stop at this point. We will later discuss the other advantages that we are going to get when we go to negative feedback amplifiers, which is bandwidth and modification of input and output impedances and so on. Okay, thank you.